Hi, I'm Nirwan and I'm doing my PhD here at UIT. So today I'll be talking about the improvement in self-attention in the context of LLMs. And it's kind of a technical topic, but I'll try to make it as non-technical as possible. So we've learned a lot about interpretability, prompting, fine-tuning, and so on. And there's still more left for the day. But now we'll just try to understand kind of the magic that unfolds behind the scenes of transformers, the kind of core concepts behind transformers. So for all our language models, there is we need it to be basically coherent. We need it to output sentences that make sense. Like for example, we can say that we want our model to output something like Japan is the home of cherry blossoms, and not just say something like food, polar charge, and not just make up random words and put them together. So this kind of training, the training that is needed to make these models output some kind of sentences, it can be divided into three basic types. The first is called CLM, which are the autoregressive models, that is the GPT and so on, the kind of decoder-only models that Abhinanda was talking about yesterday. There's also the masked language modeling, in which we kind of hide words from the models and tell it to fill in the blanks. And this way the model has context of like all the data that it has, and it just has to fill a blank. It's kind of an easier mode of training. And the last is the sequence-to-sequence modeling, in which we provide a sentence and we ask the model to output another sentence. So the problem with previous large language models that used RNNs and LSTMs was that they couldn't really, previous to LSTMs basically, they couldn't really work very well with long range dependencies, in the sense that it basically forgot what was coming before, and it kind of wasn't able to remember the context very effectively. Coming to NMT, this the neural machine translation, a paper in 2014, they demonstrated that by using a very large corpus of data, you could basically have a kind of translation model where each word is fed into the input into the model, and it gives an output. And this is kind of a huge breakthrough at that point of time, because previous to that kind of that research, we had to fine tune these kind of models by hand. And even further, a paper, they came up with the concept of attention, soft attention, basically. And they kind of used both an encoder and decoder model together to basically get the entire sentence together, and it gave better results in taskless translation and so on. And these kinds of NLP models, these translation models and autoregressive models, they have kind of a very interesting similarity, in the sense that both of them have to output words that they haven't really seen before, in the sense that we just input words and we tell them to output the next word. So now we come to transformers. Why did we exactly need these transformers? So transformers, basically RNNs, that is the machines in this picture, it is very sequential in its nature, in that we give each word at a time and it outputs the next word. And that makes it really slow. So we have very powerful hardware lying around. We have GPUs and so on. But these kinds of architectures couldn't really use the power of these machines. And so in 2017, we had the emergence of transformers, which gave us really new building blocks for these kind of machine like NLP tasks. So as you can see in this image, a transformer here is basically doing a translation task where it's converting an English sentence into Spanish. And this is kind of the overall architecture that we have, where we have an encoder block and a decoder block. This is the kind of the initial architecture of the transformer, which was introduced in the paper, Attention is All You Need. And what we have is we give our input, our sentences, and it is embedded into numbers, and it kind of the encoder is basically, it gives us the semantic meaning of these words, and the decoder, it kind of gives us it kind of generates, it's kind of a generative model. Like for example, in vision, you could say it's kind of similar to GAN, in the sense where it kind of generates words that it hasn't seen before. So this was kind of the overall idea of transformers. And I'll explain self-attention later on, but this is kind of the basic building structure of both the encoder and decoder, where we have self-attention, we have the feed-forward, which is basically just the layer which connects all the previous information together. And in the decoder, we have self-attention on the decoder itself, and also information from the encoder, all the information that the encoder has, which helps it to basically generate more useful information. So now let's come to attention. I would like to explain it to you in a very intuitive way. So example, when we see something, we have a huge peripheral vision, but we can only focus on a very small part of the peripheral vision at once. So that is the part where we're attentive to. For example, if I look at that camera, I can see all the people around it, but I cannot really, they're kind of blurred in some sense. And that is kind of the same feeling that we have, that is the same intuition behind attention, in the sense that we know everything about the words around it, but at a point of time, we focus on a single word and we try to understand how important it is in that context. For example, in this sentence, a boy is holding a blue ball, and here the blue could be the ball, like the ball can be closely related to blue and also the holding, but the blue is not related to the boy. So the blue is only related to the ball, and the language model needs to understand this kind of thing, which is where the attention comes into play. So let's consider these two sentences over here. The cat drank the milk because it was hungry, and the cat drank the milk because it was sweet. So here the word it refers to two different things in two different sentences. In the first one, it is referred to it refers to the cat. In the second one, it refers to the milk. So this is kind of the attention procedure, the attention mechanism that goes on behind transformers. Now coming to the architecture of the transformers that's being used. So when we talk about transformers, we are taking out the inherently sequential part of the sentence that we have. So we don't input words one at a time. And because of this, we can parallelize it, but at the same time, we lose all kind of positional information. We don't know which word comes earlier than the other, or which word comes later. So for this particular reason, we have to embed the position, the kind of positional information that we have of each word into the model itself. And that is done using a kind of cosine wave. We basically have a unique number for each word that we have, and it is done using this formula over here. If the sentence is large enough, it does produce unique embeddings. It almost always does, but it's not provable that it does produce unique embeddings each time. Now coming to the self and multi-headed attention. So here there is a concept called query, key, and value for transformers, which is kind of similar to the database structure that we use in SQL and so on. So thing is, we can suppose a sentence, for example, the dog chased the cat across the street. Just bear with me. So we have a sentence which is the dog chased the cat across the street. Yeah. So in this particular example, we have a sentence over here. And at each point of time, each word here, so we have three basic values, three basic concepts, which is the query, key, and value. So the query, for example, if my transformer is looking at the word dog right now, so at this point of time, this would be my query. And all the other words, including dog itself, would be the key. So it is trying to query how important each key is. It is, like, for example, the dog is most important in context to the cat here because it is chasing that. So in this case, the attention score, that is Q into K, transpose, let's assume transpose for now. This would be the value, which is our attention score basically. So in this way, we kind of, in way of matrix, we kind of scale it further and further. But in this kind of way, we kind of try to find the values, the kind of attention scores that each word has for each and every other word. And it's kind of a square matrix where we have kind of basically a diagonal matrix. So here you can see that we have a very important function over here called softmax, which we'll be referring to later on. And this is the part that takes the maximum amount of time while computation of the self-attention. And we have multiple self-attention modules, which kind of tries to find the relations between the words, different kinds of relations, I would say. Now we come to the main part of my talk, which is flash attention, or kind of improvement in self-attention. So attention itself is parallelizable, it is fast, it uses the entire GPU hardware, and it has been kind of the groundbreaking discovery, I would say, over the last decade in NLP, which helped the development of GPT and larger models, helped it to train on larger models and so on. So what flash attention does is basically it kind of improves on this attention mechanism, not in any software level, but more on a hardware level. A PhD student basically, he saw that the way that self-attention was being implemented on the GPU was very non-efficient, in the way that it was kind of a brute force method where they just put everything in the GPU, and they didn't really account for the latency issues that they were making while transferring data from one part of the GPU to the other. And for that reason, he kind of introduced flash attention. And these are kind of the perks that it has. It is up to almost 3 times fast as normal attention. And this is a huge deal. Like, this is a huge deal because LLMs take a large time, a very, very long time, and it takes a lot of resources to train, to fine tune even. And even like 3 times as efficient, it means it can save a lot of power, a lot of time, and it is very, very relevant in the field of sustainability and environmental friendly machine learning. It is also much more memory efficient in the way that it reduces the memory complexity from n squared to n, which is a huge jump. And it is not an approximation, which means that it is not a numerical like approximation method where we kind of tend to approximate the values. It is just the exact same thing just in an algebraically provable manner, and it basically just breaks the entire operation into smaller chunks and kind of does the entire thing. And the last thing is sentient. It's not really sentient, but in the sense that it uses the GPU architecture, the underlying GPU hardware really, really well. About the hardware over here, over the years, NVIDIA, mainly NVIDIA, they have been increasing the flops of the GPU a lot more than they've been increasing the general like the bandwidth speeds of their chips. So, and it doesn't really matter in this case because the self-attention that they had been using up till now, it didn't really use this flops mechanism. And for that kind of reason, because the student who made this, he couldn't really convince NVIDIA to change the hardware architecture all of a sudden, just to implement flash attention. So he kind of made up the code for this to kind of compensate for this imbalance. So coming to the GPU architecture, computations can be of 2 different types. They can be compute bound, which is matrix multiplication, which is kind of the maximum operations that we have, or that they can be memory bound, which is like elementals operations, dot products, matrix addition, so on. And it turns out that attention is memory bound, and because of this, it uses the GB per second instead of flops. Coming to this kind of study done by the student on what kind of operations take up most of the time while calculating self-attention. So in PyTorch, the self-attention is PyTorch, which is very optimized in itself. The maximum amount of time is taken by masking, softmax, and dropout, and not MACMUL, which is matrix multiplication. And in this case, the flops per second, that kind of architecture was being used by MACMUL, and that was really insignificant in the kind of time that it took to calculate the attention scores. So I kind of go over to kind of the architecture of the GPU. So the GPU has basically 2 kinds of memory. One is the SRAM, which is kind of the RAM of the GPU, if that makes sense. And it is really, really fast. It is used to store cache memory. But it is the downside is it's very expensive and it is really, really small. So it's only 20 megabytes in general. This is talking about A100 server, which has a 40 GB of VRAM, and only 20 megabytes of that is accumulated to SRAM. The HBM is high bandwidth memory, which is basically the size of the GPU that we have, which is in our case, we have A100, which is 40 gigs or 80 gigs. And the CPU DRAM, which is basically the RAM that we use in the system, which is even slower than the GPU. This is kind of the hierarchy. And in practice, the self-attention basically used the high band memory, which is the slower one, to calculate the scores. And we have to remember that these numbers, the number of embeddings used here are huge, like tens of thousands cross tens of thousands. So the amount of time it took to calculate these was magnanimous. So what was done? So this is kind of the general algorithm used for calculating self-attention. And as you can see in step 1, we compute the value, which is the V over here, which is Q into K, and we kind of write it to the high bandwidth memory. And just after that, we again read it from there. So that's kind of a wasted step over there. So there are multiple wasted steps in the basic implementation of self-attention. And so one of the things that a very basic optimization method that they have used is called kernel fusion, where they basically use many GPU operations together. They fuse them together and they kind of try to minimize time that is needed to compute the entire thing. So here we have the kind of algorithm for flash attention, where instead of writing the self-attention scores to the high bandwidth memory every time, what we do is we kind of break these query key values into small chunks, and these chunks are then calculated in the SRAM, which is really, really fast, and we kind of calculate all these together, and then we pass it to the huge storage, the huge memory of the GPU that we have. So in turn, we're just calculating all of them together, not waiting for anyone to basically finish computing. And it is a parallelization on parallelization. And after that, we kind of transfer this into the HBM and we read the values all together at once. But there are some issues with flash attention at the moment, in the sense that each attention mechanism needs the code to be rewritten. And this is basic CUDA code that we're talking about, not Python-based code. And it is not something that generally machine learning engineers are accustomed to. And that is one of the reasons why people don't really use flash attention at the moment. And there is something called OpenAI Triton, which was again developed by a PhD student. And what it does is it basically provides an abstraction layer between CUDA and kind of the other like languages that we use for machine learning engineers. And this can kind of try to bridge the gap between what it can kind of bridge the gap between CUDA language and machine learning engineers, and it can help them to kind of use this flash attention more. And the last thing is this kind of the flash attention is still being maintained by just a small group of people, and it would be immensely helpful if it is adopted by larger frameworks like PyTorch or TensorFlow. So here I kind of conclude my talk about self-attention and improvement of self-attention. And now I'll kind of talk about a web app that the group of BioAI have designed. It is called Private GPT++. And it kind of helps you to basically upload your own documents, any kind of private documents, and it runs everything privately on the server. And you can kind of use LLMs, your own LLMs, or any kind of LLM from Hugging Face or wherever, and you can kind of use it to query on your documents.
This flash attention, does it only work for transformers, or is it generic for like any?
It's not generic.
Like for any convolution?
No.
It works only
for transformers, yes.
But the issue that we are tackling
Mhm.
is of convolution. Like every time we are multiplying the matrices,
Mhm.
and then there is this intermediate operation because of which we have to transfer it back.
Mhm.
So, do you think it could be generalized to
Yeah. Even the author said that it could be generalized even to different tasks, but it requires the like rewriting of code every time. So it's not generic at this moment, but it could be. So coming to private GPT++, it is a completely secure way of using LLMs on your private documents. And it is run on our own A100 server, which is owned by UIT. And it can use almost any model that is open source. So none of your data is leaked to other companies and so on. One point about it is built just for privacy and not for speed. So it does take some time to generate results. And it can be used for any sensitive documents, any legal medical documents that we have. So this is kind of the interface, the kind of homepage that we have over here. I'll show you a video demo of how it works. And I'll just go through the pipeline first, how it works, and we can kind of try to understand it better. So at first, we have some documents that we have, and we kind of feed it to ingestion mechanism. It gives us the processed documents, in some sense, a kind of mishmash of documents that only the LLMs can understand. And the LLMs feed on this document, and within the context of just those documents, it gives us a results. As Aaron showed yesterday using LangChain, it's kind of the same mechanism. So the documents that we have, it is converted into chunks. I spoke about yesterday as well. It's basically smaller parts of text because documents can be bigger. And it converts them into a vector store, basically you could say your private library, where it only refers to the documents that you provided it. This is kind of the flow diagram that we have for GPT, private GPT++, where we basically upload a file or multiple files. There is ingestion. There's basically it's ingested using some mechanisms, and it is fed to an embedding model where it converts the words into numbers and so on. This embedding model is then converted into a vector database, our own private library, from which the LLMs shall answer the questions. And this kind of the library that we have. It is in numbers again. So this number is then fed to the LLM, which kind of answers our questions. Now coming to some very basic terminology that we have over here. I'm going to speak about vector embeddings, which is basically any kind of data that we have, image, video, text, so on. The models only understand numericals, numbers. So everything is converted into these kinds of embeddings using some kind of model or some kind of trained model beforehand. This is an example of an embedding. So a dog, it can be, in this example, there are only 7 embeddings, but in practice, there are hundreds of thousands of them. So these embeddings are, in the sense, the kind of feelings that we have when we hear these words. For example, if you hear the word orange, round, the color orange, star, sweet, these kinds of attributes come to mind. So these are kind of the kind of qualities that these numbers represent in some way. And you can see over here that these kind of word embeddings, it is in 7D over here, since there are 7 attributes. We can kind of reduce the dimensions to 2D, and we can see on the graphs over here that a puppy is very close to a dog, and that is kind of close to a cat because they're both four-legged and so on. These are kind of attributes that they have. But houses are completely different, and that is kind of, therefore, they're kind of separate on the graph over here. And the same with the second graph, where king and queen are kind of political, I would say, political establishments, and man and woman are close together, and king and queen are close together. But woman is farther away from queen, because although queen is a woman, it's kind of a part of the attribute, but still there's some difference. Now coming to yeah, this is the kind of important concept I think many people have confusion with, which is the difference between tokenization and embeddings. So the words that we have is first converted into tokens, which is numbers in some sense. And it's kind of the vocabulary that we have for each word that we hear. And these tokens are then converted into embeddings. That is the kind of qualities of each of these words. And with that, I kind of conclude my talk over here, and I would like to show the video.
Right, what you know?
Yeah.
Yeah.
So the private E plus plus,
Mhm.
is that something you have made or is it something?
It is based on a previous repository that used two models only. So we kind of modified it to use any kind of models that we have that are available publicly. And the original code didn't really have any like have any things to kind of delete the documents to upload later on. But we kind of you can upload the documents on the server and it deletes it after a specific amount of time.
Is that product documented anywhere?
Yeah.
Where?
Like I have my own repository where I've kind of made the entire thing, and that is can be made available if you want.
That's public.
Yeah.
So there is a
Yeah.
Docker file is there. If you want to run on a Docker, so Docker complete code base is there. If you run it, you can get as
This is kind of I took a video beforehand since it takes a little bit of time. So over here you can see I can choose any file, any document. It can be of any type, PDF, CSV, and so on. In this particular case, I use a study done by BlackRock on political scenarios of the world, geopolitical scenarios. And I select it, I upload it. Once it's uploaded, I give it a question. So this particular thing, it's not really mentioned in the document itself, but that is kind of a testament to the power of LLMs, not the private GPT web app itself. So it doesn't really mention which countries are at the risk of cyber attack, but it kind of tries to decipher the knowledge that it has. You can do many other things. You can basically pass many other parameters, but for now, these are the parameters that we have. And in case of model, we tested it with around 7 different models, I guess. Here we are just using Llama CPP. And after a while, we get this kind of answer. It gives us an answer and also gives us a source, the kind of source in the text from where it got these answers from. The question was, what countries are at the highest risk of cyber attacks? And the answer it gave was based on the given report. The countries that are at the highest risk of cyber attacks are US, Middle East region, Taiwan. And they've been identified as having a high risk of cyber attacks due to various factors, like geopolitical competition, conflict zones, and upcoming elections. And additionally, the report highlights that technological advancements in AI could increase the risk of cyber attacks. And below it gives us a source in the documents that it finds, from where it basically takes it kind of deciphers this kind of information from. And it gives a quite exhaustive list of the sources that it takes from here on.
And what about the quality of these resources? Quality of from where?
From the document that is uploaded.
Like from the document?
Yes, not from anywhere else. So it only has any answer that it gives, like Aaron showed yesterday. The only context that it has is from the documents that's uploaded.
Yeah.
So I try to give it another question. So I kind of give it, I ask it who are currently the major powers in the world, and the document again doesn't have any access to that kind of information. It gives us the answer again. So based on the provided context, the current major powers in the world are China, Russia, the US, Japan, and Europe as a bloc. So although it doesn't have that kind of specific information, it understands the entire documents, which is again a testament to the LLM, but not the project itself. What I'll do instead is I'll show you how it kind of works over here. So this is kind of the thing that we have. I'll show you the different models that we've used here. So these are kind of the different models that we have. GPT-4 for all is CPU-based. Phi is CPU-based. More CPU-based models will come in the future, which can always be integrated. MedLlama over here is basically for medical text generation. CodeGX and CodeLlama are for code, and Vicuna is another GPU-based model. And yeah, so this is the kind of GitHub repository. I can show you the GitHub repository. So this is the repository that I've created. It has the instructions for how to run it, but it is only accessible to those who have access to the A100 server currently. It can be run on your private systems as well. Some changes have to be made in order for that to happen. But yeah, so This kind of concludes my presentation. Thank you.